and jumps, hopefully the mass does not change. Ne? So the velocity changes. Let's see, let's make up velocities. Let's say the velocity here is 2, if we choose up to be positive. Then what would the velocity be there at C? 0. And then here at B, there it will be -2. So at B it will be like -3, 4. And then at A, like -4. Ne? Yes. Okay, so where will its momentum be a maximum? The magnitude, the size, so nothing to do with that direction, nothing to do with the negatives. Where will it be a maximum? At A, right? Because then the velocity is the greatest, so the momentum will be the greatest. A. It just tells you the direction it's going. Okay, next one. A stone is thrown vertically upwards and returns to the thrower's hand after a while. Which one of the following velocity versus time graphs best represents? Okay, the first thing you ask, velocity time, what does the gradient tell you? For a velocity time graph, what is the gradient? Acceleration. If the ball is thrown, what is the acceleration the whole time? It depends what you choose to be positive. If we choose up to be positive, it's going to be -9.8. The whole time, constantly. So can we have a change in the gradient? No, we cannot have a change in the gradient. Because the whole time the acceleration is the same, so the gradient is the same. So it cannot be A and it cannot be D. Okay? Wait, let's see. When it leaves your hand, let's say it leaves your hand at 10. We choose up to positive, so it's positive 10. At the turning point, what is the velocity? 0. When it comes back to your hand, what's the velocity? -10. So it goes from 10 to 0 to -10. So the answer is B. Then what's happening here at C? C is just when it goes to its maximum height until it goes to a 0 velocity. You see that? Drawings, notes, sketches, important. Okay, last multiple choice question there. An object projected vertically upwards reaches its maximum height and returns to its original point of projection. Like up your hand, down to your hand. Ignoring the effects of friction, the direction of the acceleration of the object during its motion is what? Let's see. So an object is thrown up and down. From the moment it leaves your hand, what is the only force that acts on it? The gravity. And what caused gravity? Gravitational acceleration. So what is the acceleration here? -9.8. Here, -9.8. Here. So the whole time it's downwards the same. So it's always vertically downwards. Sharp. Okay, now let's get to drawing graphs. On page 6. It says there, throwing a ball up and returning to its original position. Take up as positive. Initial velocity is 15. And time to its original position is 5 seconds. Okay, anyway. So we see there the initial velocity is 15. So what is the final velocity there? -15. So subconsciously we took up as positive. And as I write down that, I say the acceleration is -9.8. Right, then they say the time to its original position is 5 seconds. So 5 seconds. So what is the time to the maximum height? 2.5. The time till here is 5 because the time up is the same as the time down. What is the velocity here at the top? 0. Okay, so we have a lot of information. To original position. So from here to back to its original position. 5 divided by 2. Because the time up must be equal to the time down. Say again? No, because it's not time to height is 5 seconds. Well, it was 10. Well, yes. All right. Okay, so let's look at a velocity time graph. The first thing you ask yourself is, what does the gradient tell you? The gradient gives you acceleration. What is this acceleration? Negative. Yo, if someone gets this wrong in the test, I will be upset. I am a very passionate marker. So have you guys ever watched people playing tennis? Like Serena Williams? I'm like that when I mark. Yeah, so I mark in the middle of the night, not to disturb my children. Okay. So the reason why I make my x-axis in the middle of the graph is because I have positive velocities and negative velocities. So I'm going to be on the positive side and on the negative side. Okay, I have velocity in meters per second. I have time in seconds. Okay. Then, okay, we must get to 5 seconds. So we can make it 2.5 and 5. You can make it whatever, doesn't matter. And our velocities, we have 0 and we have 15 and we have negative 15. You can make it 10 and 20, whatever. Okay, now I'm going to plot my points. So the first point at time 0 was 15 seconds. So at time 0 it was 15 seconds. Meters per second. Dankie. Then at time 2.5 it was 0 meters per second. And at time 5 it was negative 15. How do I know it should be a straight line? It's negative, so it goes like this. And it's constantly 9.8. So it's not curvy, it doesn't change. Now, a question that they love to ask, but we've answered this question, is after you've drawn the graph, they'll ask, what does the gradient of this graph represent? Gravitational acceleration, 9.8 meters per second squared. Okay. If we look at a position time graph, now a position time graph will actually represent the motion. Like the shape that it goes in your position time graph, it should have the same shape. So the ball went up and down curvy, so you should see up and down curvy. Okay, so we are going to take the ground as our reference line. Okay, wait, sorry, did we do this multiple choice question? I just want to check. No, we didn't. Why did you say that was the last? Did I say so? Did you not tell me there's more?
I saw
Okay. Well, no, it was just forgetting. We will get to that. Let's finish this page and then we'll get to that. Okay. So we are going to take the ground as our reference line. So we don't go below the ground. So that's why I'm going to make my x-axis there. Because we don't go below the ground. In this graph, in this instance.
So maybe like if it was a breach.
Yes, then you would go below, yes. If you take the bridge as your reference point. Time seconds, distance in meters. Okay, so now the time, we have 2.5 and we have 5. But we don't have the distance that it went up. So normally when they ask you a question like this, previously in the question, you would have calculated how high it would have gone. Okay? If they don't, then you can they just want to see if you know the shape. But we can quickly go calculate it. And how do we calculate that? Y is equal to near VI plus a half a delta T squared. 15.
This is given.
Yes. Why am I not using 5? Why am I using 2.5? Because I want to know what is the height until the maximum height. Where does it go there? If I calculate, if I put in 5, it's going to give me the displacement, and it should give you 0 because the displacement is 0. Should give you. I don't know if it will in this instance because I think I just made up any numbers. Okay, so the maximum height is 6.88 meters. I'm not going to go divide it up into businesses. Right, and it's going to be loopy-loop. Why is it not going to be a straight line? Because the gradient for a position time graph is the velocity. Was the velocity the same the whole time? No, it slows down, down, down. It's stationary, it speeds up, 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 up. Okay, so it can't be constant. So the velocity goes down. The velocity decreases. It slows down, slows down, slows down. The velocity is 0. And then it speeds up, speeds up, speeds up. Okay, next one is the acceleration time graph. What was the acceleration during this whole thing? When it went up, minus 9.8, minus 9.8, minus 9.8, minus 9.8. So the acceleration is going to be a very easy graph. I'm not even going to use a ruler. It's just going to be a straight line, negative 9.8.
Do we ever get a positive?
If you choose down to be positive, then it's going to be positive 9.8. Whatever. Okay, quickly go to that multiple choice that I skipped. Okay, because they are the most difficult ones. It says, a ball is released from rest from a certain height above the floor and bounces off the floor a number of times. Okay, so we have this chop. You get the idea. The position versus time graph. Position versus time graph. Below represents the motion of the bouncing ball from the instant it is released from rest. And it's released from a certain height. Okay, so if I were to draw my picture, From there it's released and then it goes down, up, down, la, 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 la. So I just said a position versus time graph gives you the shape of the motion, or it shows the motion.
This is upside down.
It's upside down. So what did they do here? They chose down to be positive. Okay, how did they choose down to be positive? Because then it goes in the positive direction and then it goes in the negative direction. Positive direction, negative direction, positive. And they chose from the certain height, they chose that height to be 0. So they said this is 0 and then it goes in the positive direction 3 meters. So then that would be 3 meters. You see?
Yo.
So it's a reverse. So this is the ground, or this is where it bounce, and this is where it bounces. It touches the ground. This here is the maximum height. And then this here is also the maximum height after the first bounce, and maximum height after the second bounce. Okay? Right. Now they ask, in neglecting air resistance, which point A, B, C or D on the graph represents on the position time graph coordinates the maximum height reached by the ball after the second bounce. So there's my first bounce, there's my second bounce, the maximum height that it reached is D. So if you know how to read the graph, it's easy. And then the shape of the graph will look a bit different. But you will always neglect the air resistance. Okay. Next one. A ball is released from a certain height above the floor. My goodness, again, the same scenario. And bounces off the floor a number of times, ignoring the external resistance. Which one of the following? Velocity versus time. So here we had position versus time. So that's why the shape looks like the bouncing ball. This one is velocity versus time. It's not that. Velocity versus time graph represents the motion of the ball. Right. What does the gradient tell you? The gradient gives you acceleration. What is the acceleration? 9.8. Positive or negative? They didn't tell us which one did they choose to be positive. In which direction is the ball going first? Down. So I'm hoping they chose down to be positive. So it's positive 9.8. And a positive 9.8 gradient looks like what? Positive gradient looks like this. Ne? And it's constantly the acceleration, the acceleration is constantly 9.8. So it means the gradient is constantly the same. Okay? So we're thinking this. So immediately A and B is gone because they're the gradient wiggly woggly wiggly. Okay? Why is it not D? This tells you the velocity is the same. Not the acceleration is constant. The velocity is 10, and then the velocity is negative 10, and then the velocity is 8, negative 8. It's not that. The velocity changes because the ball goes slower, faster. Right? And it tells you the initial velocity is 10 or whatever, and it tells you it's from rest. The ball's dropped from rest. Positive gradient. Now what's happening here? Here it's where it's in contact, the ball is in contact with the floor. Okay, so ball falls, contact with the floor, and then so if we say it is 1 second here, and then also in 1 second it's going up. You see that? So that is why there's a break in the graph, because here the ball is going down, it bounces, and the ball goes up, ball goes down, bounces, ball goes up. Wait, what? When is the velocity 0?
It's maximum height.
At its maximum height. So when the ball is there, the velocity is 0. So when the ball reaches its maximum height, it's 0. And then what happens after that? The ball goes down again. Ball goes down, 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 down. Bounce. Ball goes up. Ball goes down, bounce.
Choose the direction.
Because we chose the direction down. Now, this here is acceptable. You might do something like this. But what we actually know is when this ball bounces, doesn't the moment it reaches the floor go up again? No, there's like a split second or whatever that is in contact with the floor. Alright, so there should actually be a gap here. There, and then a bit of a gap to go on there. So what they should say here is ignore the time that the ball's in contact with the floor. Okay? When you have a hard ball, then it is quite little, the contact time. When you have a soft ball, then what happens is you'll see the ball actually goes whoosh, and then it goes up again. Alright, so if you have a soft ball, the contact time will be much longer. I want to say something else here. No, I think that was it. Okay, so our answer there is thus C. Then the last one there, they say a 30 kilogram iron sphere, iron ball, iron round thing, and a 10 kilogram aluminium sphere with the same diameter. Diameter just means the same contact that it has with the air. Falls freely from the roof of a tall building. Ignore the effects of friction. When the spheres are 5 meters above the ground, they have the same what? Okay. Okay, obviously yes. Acceleration. Let's just check one, not the others. Momentum is mass times velocity. Are the masses the same? No. Kinetic energy is a half mv squared. Masses not the same. Potential energy is mgh. Masses not the same. Right, good. Back to the graphs. Yes. Okay. All right. Next question. It says then, throwing a ball up and returning to a position lower than the origin. So throwing it up and it goes down there. I tell you the initial velocity is 3.7. Time to the ground is 1 second. The girl's height is 1.2 meters. So the girl is probably in grade 7. Not grade 1. How tall are you?
I never say grade 1, but
I'm 5'7".
I don't know.
Yeah, but how many meters?
How many meters is it?
I don't know.
Grade 5. Mama, do you know how to
1.6. But I didn't grow much since grade 10. Alrighty. Okay, they say take the ground as reference point. Okay, let's quickly draw here in. We have the initial velocity is 3.7. So we subconsciously took up to be positive. As I write that down, I say that means the acceleration is negative 9.8. What's the velocity at the turning point? 0. We don't know what the velocity is here at the end, but we do know that it will be greater than 3.7. Like the magnitudes, right? It will be 6 or whatever, and then it will be definitely be negative.
So isn't that supposed to be the other?
Yeah, but I what I mean is the magnitude, the absolute value. We done absolute values? Absolute just means the positive value of whatever is given. Alright, the time to the ground they say is 1 second, so time to this 1 second. And then this height there is 1.2 meters. Okay, so Karabo asked, can we say the time to here is 0.5? That was what you asked me.
Height is not the same.
Well, okay, alright. Never mind, she realized she made a mistake, so she didn't ask that, but I'm asking it. Is the time to here 0.5?
No.
No, because it didn't go from here to there. Okay. Right, so when we have to draw, sorry, a velocity time graph, you ask yourself, what does the
Was it positive for the small?
But it doesn't matter if you draw it at the middle, it's not the end of the world at all. Okay. Our initial velocity is 3.7 when time was 0. And that's all we have. We can calculate other things. Even they ask it from just that information, the only other thing that we can put in is we can say when the time is 1 second, we have a value. We don't know what the value is, but we have a value. It's going to be negative. And what shape will our graph look like? Like this, negative gradient and constantly. So I'm just going to draw this with a negative gradient until 1 second. That's all I can do.
Doesn't it have to touch the one?
No, because the velocity is not 0 at 1 second. The velocity is greater than whatever, but I don't know what it is.
You said it's decelerating. And your head's going backwards.
That's accelerating backwards, yes.
And then here, it's going backwards. It's not decelerating. Position time.
Yes. Okay, you can see that I do not elongate it after 1 second. Because our scenario stops, the ball reaches the ground 1 second, and it doesn't say it bounce or anything like that. So don't make it longer than 1 second. Okay. And what you can do is you can obviously just show them that there is 1 second. Okay, position time graph. Now let's ask. I haven't even started with questions today. Bluntly. Tell me, do you want to take the goal as reference point or do you want to take the ground as reference point?
Take the ground.
Okay, she's taking the ground as reference point. So that is my 0.
Now I'm
Isn't that going to be harder?
No.
It's the same.
If the goal was my reference point, my thing would be here.
Yes.
And then my graph would look like this. And now my reference point is here and my graph is going to look like this. Same thing.
Would they tell us what graph to draw?
Yes. Say again?
Not very.
Okay, again, we do not have a lot of information. We have the goal is 1.2 meters. So we know we should start at 1.2 meters. And it says it ends at 1 second, so we end at 1 second. And what will the shape of our graph look like? Up and down. And what is our acceleration?
Acceleration has to be the base.
What test? Well, you're gonna write it in your register classes, if I'm not mistaken. No. Oh, I can't remember. I know some people are writing in the gym hall. Can't remember who. But because we go on with class, we can't take all of the tables to the hall, and then after that you have to go back to your classes. It will be the last time that, if you write in class, it will be the last time. From June, you'll always write in the hall. Always, always, always. Okay. Next one. Now, this one is the most difficult one. Okay, it says the ball is dropped to the ground and it bounces back. Okay, like you just did in multiple choice question. Time to the ground is 1 second. Height from where it is dropped is 2 meters. Take the ground as the reference point. Okay. Now, what did I want to say? You see here we have two types of ball. We have a hard ball and a soft ball. Again, I didn't put in an acceleration time graph because it will look exactly the same as the previous two. Okay. A hard ball just means the contact time with the ground is small. So we're going to ignore that contact time with the ground. I just want to check here. Okay, so you know the booklets that you're supposed to think? Yeah? Yours does not have these summaries in. I have no idea why not. That is why I put the summaries in your notes. Okay, so what they say there here with the hard ball is that if the ball is, let's say, it reaches, so it's dropped, so it means the velocity here is 0, okay, and let's take down to be positive because the first motion is downwards, yes, then the velocity with which it reaches the ground is, are we going to make one up? 5. Then they say if it is a hard ball, then the velocity with which it reaches the ground, if it's 5, then the velocity going up will be -5. So it means it won't lose any energy. Okay, now I do not completely agree with that, but that is what they say. I will say it does lose a bit of energy because it's not an elastic collision. Anyway, let's do it as they say. Okay, so then the velocity with which it goes up is -5 until it reaches its maximum height, which will be 0. Okay. Now, the position versus time graph. Let's just check. It's going down, right? Which direction did we choose to be positive? Down. So then, if we say there, it should go to the positive. Oh, and then what do we take as the reference point? Do we take the person's hand as the reference point or the ground? They say take the ground as the reference point. Okay, so ground as reference point. So it goes when it goes down like that. It goes in which direction? The positive direction. And the ground is the reference point, meaning the ground is our 0.
So it's gonna be like this.
It's gonna be like this. Yeah.
But it doesn't start at the ground. It doesn't start at our reference point. So it goes to the ground, to the 0, and it goes up. So we start at the negative. So wait a minute. I'm going to draw it quickly.
What?
So we start up. No? So we start in the negative. We start in the negative. How far did it drop? 2 meters. So you start in the -2 meters. And then it goes in the positive direction. So it goes in the positive direction to 0, to the ground. And then it is dropped again. Not dropped again, then it goes up again.
next point is gonna be a negative
Can you
1.
do that again?
So what was the 5?
The 5 velocity is going to come in with the velocity time graph. We're busy with the position time graph. Okay, so let's just check again. They said ground as reference point. So ground was me as 0. We chose down to be positive. So if it goes down, it means it goes to the positive. In the positive direction, our graph. Yes. Okay, so let's do it from the ground. Okay, so let's ignore this first part. If the ground is a reference point, it goes from the ground in the negative direction. So it goes from the ground in the negative direction. If we chose up to be positive, it would have looked like that. Okay? So because we chose down to be positive, so if we chose up to be positive, it's going to look like this. Because I wanted to make it difficult so that you know. Because they can ask it like this. And then you must know, what did they do? Okay, are you with me? Okay, so for the softball, we can maybe change it around if you want to. Okay, let's look at a position versus time graph. Not position, velocity versus time graph. What does the gradient tell you? Acceleration. What's the acceleration? Positive. 9.8. Why is it positive? Okay. And it goes in the positive direction and it goes in the negative direction. So that is why our line would be in the middle. Yes. Now the 0 is the ground. Take ground as reference point. So it goes to the ground and then it goes up to the hand.
So if this is negative.
Because we said up is negative. So if it goes up to the hand, it goes to the negative.
So if this is the end is the reference point, how would you graph it?
If the hand was the reference point, then like that. Because if the hand was the reference point, it would go down to the ground, go in a positive direction. All right. Velocity versus time.
What about this graph?
Now, so normally these graphs they give to you, and then you must decipher them. Yeah. We will see if it's better. All right. Let's see. Our first, when time was 0, the velocity was 0. Okay, so when time was 0, our velocity was 0. Then time to the ground was 1 second. So at 1 second, the velocity was 5. I'm just filling it in as I go on. Then also at time 1 second, because we know when it's a hard ball, it's like it goes in a. So if this is time 1 second, then this is time 1 second. So time 1 second, it's also negative 5.
As soon as it touches,
And then somewhere after, we don't know how many seconds, but I assume 1 second, it's going to be 0 meters per second.
is it like that multiple choice again?
Yes, yes. So we know it's a positive acceleration, so it's a positive gradient, so it's going to look like that. So we have our positive gradient, and then when it's in contact with the floor, it bounces, and then it goes up again. Okay, and obviously this is now where our story stops, but it can go there, and then it bounces again, and up again, and bounces again, and up again, and bounces again, and up again. Alrighty. So for a softball, I'm quickly going to do this because I want to tell you your homework. For a soft ball, no wait, maybe I shouldn't do this quickly. What did we want to do with the soft ball again? We wanted to change the direction. So for the soft ball, we're going to choose up to be positive. Are we still making the floor our reference point? Oh wait, that was the instruction. Take grounds. So we can't change that. It was the instruction. So we take up to be positive. So it went in the positive, no, in the negative direction, eh? So it went down, 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 eh? Because the ball went down, 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 and then it stayed there for a few seconds. Not a few seconds, a second, because it's soft. It goes and it squishes, and then it goes back up. So it will go down. It stays there for a minute, and then it goes back up. Okay, so it will go down, stay there, go back up. Well, and sorry, and it will not go up all the way, because if it's a softball, it will lose some of its energy. Okay, then, so this again will be -2 meters. I just want to check. I feel we're missing something. We chose up to be positive. The ground is still our reference point. So up is positive and it goes down. And the ground is our reference. No, it's fine. Yeah.
Yes, I see.
The ground is our reference point.
Oh, that's true. It's true. Yeah, I gotta say, yeah, something is nie lekker nie. Hi. So. Sorry, Eda.
So positive 2.
Positive 2, yes. Okay, and now in our velocity versus time graph, our acceleration is -9.8. So our gradient should look like that. Okay, it's not going to be exactly the same because some time is lost with contact with the ground. So your graph would look like this. It goes to from the hand. Oh, here, my kop kan nie. So it's going to be at time 0. At time 0, the velocity was 0. Ne? Then at time 1 second, when it reaches the ground, the velocity was -5 because we chose up to be positive. And then say at time 1.1 second, because we lost some time with contact with the ground, it goes up, but it's not going to go up with 5 because it lost some energy, it lost some velocity because it is squishy. So the velocity up is, let's say, 4 and +4 because it goes up. So it's dropped from your hand. So it dropped, the velocity is 0. When it reaches the ground after 1 second, the velocity is -5, negative because down is negative. Then it is at the ground for 0.1 seconds and then it goes up again. So that's it. At 1.1 seconds, it goes up. And because it's soft, it lost a bit of energy. So that's the velocity up is not 5, but 4, 3, whatever you want it to be. So we have...
So when it goes back up, when it back down, it's not going to be 4.
Yeah, it's again going to be -4. And then when it goes back up, 3. So we have, and our shape did we say? Yes. So we have 0 and 0. And then we have, let's say at 1 second, it is -5 there. Then at 1.1 second, it is 4 there. So we have down like this, and then somewhere it's going to be down like this again. Dotted lines like that, and dotted lines like that. So there's a time lapse, there's time missing. Okay, take a tissue. Okay, now like I said, they don't actually ask you to draw this graph, you must more decipher the graphs. Okay, anyway, so to practice more calculations, I want you to do for homework, please, 10, 11, and 12. 10, 11, and 12. And the answers are given to you there, so you can check yourself. Right, the bell's going to ring, so you can back away.